you currently working on a particular topic or have some questions in mind?
Yes, let's talk about the periodicity of physical properties. Let's pick period 3 as an example. Let's talk about melting points and boiling points.
All right. As you move across period 3 from sodium to argon, melting and boiling points generally increase up to silicon, then decrease from phosphorus to argon. Metals like sodium, magnesium, and aluminum have high melting and boiling points due to strong metallic bonding. Silicon, a metalloid, has the highest melting and boiling points in period 3 because of its giant covalent structure. Nonmetals like phosphorus, sulfur, chlorine, and argon have lower melting and boiling points due to weaker van der Waals forces. Got any specific questions about these elements?
Yes, so let's talk about what really happens when you're melting a compound. Let's start with the metals. Are you breaking apart the metallic bonds? What happens when you boil a metal? Do the atoms vaporize? What really happens there?
When you melt a metal, you're indeed breaking apart some of the metallic bonds, but not completely. Metals consist of a lattice of positive ions surrounded by a sea of delocalized electrons. These electrons act as a glue, holding the metal ions together. As you heat a metal, the ions vibrate more vigorously until they have enough energy to overcome some of these interactions, causing the metal to become a liquid. The electrons remain delocalized, which is why metals can still conduct electricity in their liquid state. When boiling occurs, it's a different story. The metal atoms gain enough energy to break free from the liquid state completely, overcoming the metallic bonds. This leads to the formation of metal vapor, where atoms or clusters of atoms exist in the gaseous phase. Boiling requires much more energy compared to melting due to the need to overcome all the attractive forces in the liquid.
Okay, so what affects the strength of a metallic bond?
Metallic bonds are influenced by several factors. Number of valence electrons, more delocalized electrons, contribute to a stronger bond. Transition metals with more valence electrons typically have stronger metallic bonds. Number 2, charge of the metal ions. Higher positive charge leads to stronger attraction between the ions and the sea of electrons, strengthening the bond. Number 3, size of the metal ions. Smaller ions pack more closely, resulting in stronger metallic bonds due to the proximity of the positive ions to the electron cloud. These factors combined determine the overall strength of a metallic bond in a given metal.
Okay, that's great. So what happens when we melt giant covalent structures? Are we breaking apart the covalent bonds?
Not quite. When melting giant covalent structures like silicon dioxide or diamond, you're not breaking the covalent bonds. Instead, you're overcoming the much weaker intermolecular forces holding the structure together. This is why such substances have very high melting points. It takes a lot of energy to disrupt their extensive networks. For instance, melting diamond would require breaking its strong covalent bonds, which is practically impossible under normal conditions.
Can you come again on this one? Are we not breaking the actual covalent bonds when we're melting such structures as diamond?
Sure. When we melt giant covalent structures, we are breaking the weaker forces between the atoms, not the strong covalent bonds themselves. In structures like diamond, where each carbon atom is covalently bonded to 4 others in a 3D network, melting would overcoming the entire structure, which is extremely difficult. That's why diamond doesn't really melt under normal conditions. It sublimes, turning directly from solid to gas.
Okay. So let's move on across that period. So as you move into simpler molecules, what are you doing when you melt or boil such substances?
Sure. As we move across period 3, from giant covalent structures like silicon to simple molecules, we encounter substances like phosphorus, sulfur, and chlorine. When melting or boiling these, we're primarily overcoming intermolecular forces, not breaking covalent bonds. For example, sulfur forms S8, Sk, And when melting sulfur, we're breaking these rings apart into smaller segments, not breaking the SS covalent bonds. With substances like chlorine, Cl2, you're overcoming van der Waals forces between the molecules, not breaking the Cl to Cl covalent bonds. The energy required to melt or boil these substances is significantly lower compared to giant covalent structures or metal.
Okay, so what are the factors? Do such factors as atomic radius, shielding, or ionic charge affect these melting and boiling points? Can you summarize on that?
Sure thing. In simple molecules, the melting and boiling points are primarily influenced by intermolecular forces. Here's how it breaks down. 1. Intermolecular forces. The stronger these forces, like hydrogen bonds, dipole-dipole interactions, or London dispersion forces, the higher the melting and boiling points. Molecular size. Larger molecules have more electrons, leading to stronger London dispersion forces, which increases these points. Shape. Molecules with shapes that allow for efficient packing have higher melting points. Polarity. Polar molecules have stronger dipole-dipole interactions, raising both melting and boiling points. Atomic radius and ionic charge influence these factors less directly in simple molecules compared to giant covalent or metallic structures. Anything else on this topic you're curious about?
No, let's continue this in the next conversation. Thank you.